The global internet is a physical patchwork of submarine optical cables, terrestrial microwave relays, and copper wiring, managed by millions of competing routers. Despite this physical heterogeneity, a block of raw data generated on a smartphone in Tokyo travels across the planet and arrives intact on a server in New York. Early computing systems required exact physical compatibility. If the transmitting and receiving hardware were not perfectly matched, communication failed. Global interoperability relies on a software architecture of rigid abstraction layers to manage this physical complexity. This animation illustrates the two primary frameworks for that architecture: the theoretical 7-layer OSI model and the functional 5-layer TCP/IP suite. TCP/IP became the global standard through its reliance on the end-to-end principle. It places the complex processing intelligence at the endpoints of a connection, keeping the core of the network simple and fast. Within these stacks, the rules are absolute. Each layer provides a service to the layer directly above it, consumes the services of the layer below it, and is entirely blind to the rest of the system. To understand modern network engineering, we have to track the exact mechanical sequence of a single payload as it descends the stack, traverses the physical network, and ascends at its destination. The process begins at the application layer, layer 5 in TCP/IP. A program generates raw data, such as an HTTP GET request for a web page. When raw data drops to the transport layer, it is classified as a Service Data Unit, or SDU. The transport layer wraps a distinct header around the front. This applies TCP or UDP, sequences data, and assigns port numbers to track the application. With the addition of this transport header, the encapsulation begins. The entire unit is now a protocol data unit, officially referred to as a segment. At this stage, the segment knows which application process it is tied to, but it contains no instructions for navigating the global internet. The segment is passed down into layer 3, the network layer. Here, the network layer wraps an IP header around the entire segment. This new header contains the logical source and destination IP addresses. With encapsulation complete, the unit is now a datagram, universally referred to as a packet. This IP packet is the foundation of connectionless routing. It contains all the necessary logical information to reach its ultimate destination independently, without relying on a pre-established circuit. The packet is now globally addressed. However, logical addresses cannot force electrical signals across copper wire. It still lacks the mechanical instructions to cross the physical hardware immediately outside the host device. The packet descends again into layer 2, the data link layer. The data link layer attaches a header containing physical MAC addresses, which dictate the specific local node-to-node hop. It also attaches a frame check sequence trailer to detect corruption. This final encapsulation creates a complete frame. The frame is then handed to layer 1, the physical layer. Its singular job is to translate the logical frame into pure binary, converting it into electrical voltage, radio waves, or pulses of light. These physical signals are then injected directly into the physical media for transmission. The abstract application logic has been successfully converted into pure physical energy traveling across a wire. Once on the wire, there is a strict separation between physical topology, how cables and nodes are physically arranged, and logical topology, how the data flows across them. The bits travel across a local area network, often utilizing a physical star topology to arrive at a local network switch. A network switch has a highly specific, limited function. It operates exclusively at layer 2. The switch intercepts the frame, scans only the MAC address header to identify the port, and forwards it instantly, ignoring the IP packet inside. Because MAC addresses are strictly local, they cannot cross independent networks. To leave the local area network, the frame must hit a router. A router operates at layer 3, the network layer, to navigate wide area networks. When a router receives the frame, it strips away the layer 2 MAC header and trailer, reading the exposed layer 3 IP packet to calculate the optimal network path. It re-encapsulates the packet inside a brand new MAC header and fires it out into the physical mesh topology towards its final destination. The system maintains order across billions of connections because hardware devices strictly respect their designated layer boundaries. Eventually, the signals arrive at the destination host's network interface controller. This triggers the decapsulation pipeline. The physical layer receives the raw bits and reassembles them back into a frame. At the data link layer, The system verifies the MAC address and runs the error check. The frame header and trailer are then stripped away. The network layer verifies the destination IP address. Because the packet has reached its final destination, the IP header is discarded. The transport layer sequences the segments, directs the payload to the correct application port, and the TCP header dissolves. Through this precise process of stripping abstraction layers, the raw data is handed to the destination application in the exact state it was generated. The longevity of the OSI and TCP IP models comes down to strict, uncompromising modularity. A Layer 3 router processes packets efficiently because it never needs to know whether a payload is a video stream or a text file. A Layer 1 fiber optic cable simply transmits light pulses without processing the IP addresses they represent. This separation of concerns allows engineers to upgrade hardware, like transitioning from copper to fiber, without requiring changes to the global IP protocol. By separating physical topology from logical routing, network engineering allows billions of disparate devices to function as a single, cohesive system.